It's been a lot of material. It's now time to see if you understand something. So you have to do some work. So here's a little quiz. So imagine there is free entry of fishermen in the fish market, the fish industry, and the stock of fish is at steady state. Now we change something. Trawling is invented, so alpha increases. Question 1, what happens to the stock of fish in the new steady state? Question 2, what happens to the intensity of harvesting, defined as the number of boats multiplied by their efficiency, so it's alpha multiplied by B star F in the new steady state. What happens to total harvest in the new steady state? Then other questions, is there a technology level alpha so large that it would drive steady state fishes to extinction? And is there a technology level alpha so large that it would drive steady state harvest to zero? So you can answer this question on this website or just do them on your own. Pause the video, and when you're done, unpause and we can correct the questions. So I invite you to use the formulas we have found and the graphs, they help. Time's up. What happens in the new steady state for the equilibrium stock of fish? Well, it's not that difficult. We just plug in the formula we had. So we had that S star F equals to C divided by alpha P. So obviously it decreases. So that's not difficult to imagine. So if there is better technology, then even if the number of boats didn't change, then they would fish more efficiently, so they would catch more fishes. But there's also the fact that if they fish more efficiently, then they make a positive profit. So more boats will want to enter the market. This will even drive even lower the equilibrium stock of fish in the ocean. What happens to the intensity of harvesting? So again, the same strategy. We have to look at the formula we had. So we know that this is, so alpha B star of F is going to be equal to alpha multiplied by the value of B star of F, which was R divided by alpha times 1 minus C divided by P alpha K. And then what can we see? Well, we see that here it's going to cancel. So the impact on the number of boats was ambiguous, but the impact on fishing intensity is not, because there's one alpha that disappears. So evidently, fishing boats are going to try to fish more, and or there's going to be more fishing boats. So this is going to exert more pressure on the fish population. Now, what happens to the total harvests in the new steady state? Well, I can simply plug in the formula for harvest. So we had that H star F was equal to alpha B star F S star F, and was equal to, then I can just plug in, so alpha B star F is this, and multiplied by S star F. And what do we see? Well, not that much actually. Why? Because here, if alpha increases, then this is going to depress H, but there's a minus there, so the intensity is going to increase H. So that's the ambiguity. It's that harvest intensity increases, but S decreases. So the total harvest, it looks like it's ambiguous. And actually, to see this more clearly, we can look at the graph we had before. So that was our graph. So what do we see? We see that fishing intensity here is alpha B star F, and it's the coefficient that multiply ST. So this line, this red line here, has a slope alpha B star F. So if fishing intensity increases as a result of alpha increasing, then it means that this slope, this line is steeper. So what's the impact on harvests? Well, we have to look at what is harvest on this graph. So as you may remember, this delta ST was the natural increase in the fish stock if there is no harvest, and it described this. It was described by this blue line there, tau of ST. But the thing is, there is harvest too. So in the steady state with the fishing industry, then it has to be the case that tau ST equals fishing alpha B star F ST. And so the steady state is here, but also the natural reproduction rate or the natural growth rate is this quantity, and it is exactly equal to the amount of fishing. So if you want to look at what is the harvesting in the steady state, well, it's just this value there. So what happens when fishing intensity increases? Well, if it's just a small increase, or let's say we start with a very bad technology where we were like here. So imagine we fish with our fishing lines and with not so advanced technology, and then we invent better fishing boats. So we are going to harvest more. But imagine that from here, then we invent trawling. So we are super efficient at harvesting, and this line goes maybe until there. And you see that if the red line is there, then the equilibrium harvesting is going to be lower than before. So the equilibrium harvesting is a function of both the equilibrium stock and the fishing intensity. And you see that if there's too much intensive harvesting, then the stock decreases too much. So the net effect is that we catch fewer fishes because there are so few fishes to catch. So that's exactly what we saw at the beginning of the class. All right. 4, is there so here I can, here let's answer. So answer increases. So here ambiguous. Positive, yeah, no, let's say negative for large delta alpha. So delta alpha is the increase in efficiency. So if the increase in efficiency is too large, then the impact on harvest is definitely negative. 4, is there a technology level alpha so large that it would drive the steady state fishes to extinction? Don't know what you, maybe with what we have now here you can answer. So the answer here fortunately is no. Why? Because this is steady state fish stock. And you see that how high does alpha have to be for S to be 0? Then alpha would have to be infinite. So this may look surprising because we said that, yes, if fishes don't reproduce fast enough, then they may just die off. But the thing is, there's also the fact that So if you have only 2 fishes in the ocean, then good luck catching them with your fish, even if you're with your fishing boat, even if it's extremely technologically advanced. At some point, the effort you have to put to catch the last few fishes is just not worth it. So there's no way that an industry can make a profit and catch all fishes. Because if you don't have fishes in the ocean, then the industry collapses and everybody does something else. So there's this natural mechanism that, at least in this model, makes it sure that no species ever goes extinct. So are you happy with what I'm telling you? Or do you think maybe I'm missing something? Well, if you have been aware a bit of species extinctions in the last 20 or 50 years or 100 years, then you may think that there is something fishy about what I'm telling you, pun intended. So what's up with that? Well, if there are only 2 fishes in the ocean, so maybe they are hard to catch, but they have a hard time finding each other too to reproduce. So in reality, the fact is maybe there's something like a minimum number of fishes, or in general a minimum stock of a certain species to make sure that the species is viable. And even more, so it's one thing to have at least 2 individuals reproduce, but then even geneticists say that you need some large enough number to guarantee diversity in the genetic material. So it's not that clear in reality whether this model reflects everything. And in fact, we're going to see later on in the class that this may be, so it's something that we can input in the model to make it more realistic. All right, last question. Is there some technology level alpha so large that it would drive steady state harvest to 0? Well, let's now look at what steady state harvests are. So it's so harvests equal to this. So again, is there some alpha such that steady state harvests are 0? Well, no. If alpha is very large, then this tends to 1. So, but it's impossible that this fraction there goes to 0. It can become very small, but not 0.